Hello dear colleagues, today I want to present my project about Mtdna mammalian evolution, mice evolve by many little steps, while elephants with a few big ones. At this project we will talk about an evolution rate, and first of all I will talk about one primary life history trait that influences the molecular evolution rate. This is a generation time effect. Theory predicts that animal with a shorter generation time, in our case it's a mouse, gets more neutral mutation faster because of the accumulation of more DNA replication per unit time. We can see that in the picture. The smaller the mass of the animal, the greater the number of synonymous mutations will we have per unit time. Many studies based on this theory consider only the nuclear genome, but we don't know what's happening in the mitochondrial genome. Mitochondria, compared to the nuclear genome, it's semi-autonomous organelle, and theoretically we expect that the replication rate of mitochondrial genome can be completely independent of the replication rate of the nuclear DNA. Another life history trait that affects the evolution rate is purifying selection. The change of purifying selection is relaxed in a low population size animals like elephants. We expected fixation of numerous non-synonymous slightly deleterious variances in these animals. And let's talk about our hypothesis. They said increased level of mutagenesis in mice and a reduced purifying selection in elephants leads to the same evolution rate in mitochondrial genome. Let's take a look at the simple phylogenetic tree, which we can see here. And we have a mouse, elephant, and common ancestor, which is here. From common ancestor to mouse and to common ancestor to elephant, we have the same number of million years. And if we analyze, we can predict that pattern of substitution should be different from common ancestor to mouse and common ancestor to the elephant. The mouse is characterized by a higher mutation rate per unit time. So in the case of a mouse, we have more mutational events compared to the elephants, which is marked as a red arrows. And each substitution is evolutionary neutral or slightly deleterious because of effective purifying selection in the mouse. In the case of the elephant, it's opposite. So the number of events is decreased because the mutation rate is decreased, but each fixed event can be more deleterious. We expect the pattern of molecular evolution should be different between high population size animals and the low population size animals. To test our hypothesis, we took two datasets. One dataset contains codon alignment of mitochondrial genes cytochrome B, and the second dataset contains information about generation length. And let's take a look at our results, at our first graph. Here we analyze the contrast between the pairs of our species. We calculate the difference between generation length of the first and the second species, and we have done the same with KS. If our two species, let's imagine mouse and elephant, if we subtract from the mouse the elephant generation length, we will get a negative contrast in generation length, and we expect positive KS. We see these dots in our plot in the second quarter. If we do the opposite subtraction and we subtract from the generation length of the elephant generation length of the mouse, we will get a positive contrast in generation length and negative contrast in KS. Most points should be in the second or the fourth quarter. If we connect them, we will get a negative correlation. When calculating such contrast for each pair, we will get this plot. In the next graph, we see a completely opposite picture. If the contrast in generation length is negative, then the contrast in KN will also be negative. We see that in the third quarter. If the contrast in generation length is positive, then the contrast in KN will be positive. We see that in the first quarter. Most points should be in the first or third quarters. If we connect them, we will get a positive correlation. When calculating such contrast for each pair, we will get this plot. And now we know that elephants have more non-synonymous substitutions. But now we need to show that these substitutions are more radical. To do this, we'll use the Graham distance. As we can see in this graph, the greater the difference in generation length, the greater the relative distance of Graham will be. Let's move on the conclusions. We observed that great accumulation of synonymous mutation in short-lived species, while long-lived species have greater accumulation of non-synonymous mutations. Long-lived species tend to accumulate more radical amino acid substitutions than short-lived mammals. Also, power of purifying selection is weaker in elephants. This is the end, and thank you for your attention.